Good afternoon, everybody. Hi, everyone. Hi, Rashmi. Hi, Ujjwal. Hello, Ruhul. I hope all of you are doing great. Okay. So this is our, one second, just 1 second. Yeah. So we are going to start with a new chapter today for chemistry, and that is the atomic structure chapter. Okay. All right. And we will be having 2 sessions for this particular chapter. And the first session will deal with the general aspects of atomic structure. The most important topics that we need to cover are Heisenberg uncertainty principle. We will cover the significance of de Broglie wavelength. After this, we also talk about the energy levels that are involved when we talk about Bohr structure of the atom. Okay. Now, in the next session, we are going to cover the electronic configuration part. Okay, electronic configuration. So I hope you guys will come prepared in the next session for this particular topic specifically. Okay, so moving forward, Heisenberg uncertainty principle. So it says that simultaneously it is impossible to determine the exact position and exact momentum of an electron that is revolving around the nucleus. That means there would be some uncertainty when I try to determine the position, the exact position, and exact momentum simultaneously. So the product of these uncertainties is given as greater than equal to h upon 4 pi. Okay. Now, when we need to solve the numericals, when these uncertainties are provided to us, what do? We make this inequality sign as this. We just put it equal to this. We put the value of h, we put the value of pi. H is our Planck's constant. Sorry, Planck's constant. Okay. Now, an interesting part is this is momentum. We can write this as delta m into v. Momentum is mass into velocity greater than equal to h upon 4 pi. Now, after this, we know that the mass of electron is going to remain constant. So we can take out this m out of the uncertainty bracket and we can write down m delta v greater than equal to h upon 4 pi. All right. Okay. Now, let's say in a particular question, in a particular scenario, we have been given that the uncertainty in determining the position of the electron is 0. That means we know the exact position of the electron. Exact position of electron is known to us. So what do we do? Yeah. So what do we do? What is the uncertainty that would be there in determining the momentum? What will be the uncertainty there? Yes, Farheen. This is 11th class chapter. Yes. So delta x into delta p is greater than equal to h upon 4 pi. That is what we have. If delta x is given to me as 0, there is no uncertainty in determining the position. So the delta p, the uncertainty in determining the momentum, very good Meenakshi, will be infinity. Okay, it will be infinite. Okay, hi Abdul, good afternoon. I hope this much is clear to all of you. Next, we talk about the validity of Heisenberg uncertainty principle. So there are two kinds of objects, broadly speaking. We can have microscopic objects, where we talk about the electron, the subatomic particles which are there. Then there are macroscopic objects. Okay, so can I just say that Heisenberg uncertainty principle is only valid for microscopic? No, we cannot say that. So it is valid for both. Microscopic are छोटे particles. Macroscopic, macro means big. Okay, so these are the bigger particles, bigger objects that we have. Okay, so it is valid for both, but is it significant for both? So significance of Heisenberg uncertainty principle, it is only significant only for microscopic objects. Okay, it is only for microscopic particles, that is electrons or subatomic particles. Exactly, very nice, very nice. Okay, for macroscopic objects, what happens if we tend to apply the Heisenberg principle there? Then the uncertainty in position, or the uncertainty in the momentum that we get, it is too small to be considered. Like, it's negligible. Okay, it's very, very small there. Meghna, the Heisenberg uncertainty principle can be applied to microscopic smaller particles as well as macroscopic, the bigger objects, like a football. You can apply it there. Okay, when a football is in motion, we can apply it there. But for a macroscopic object, the Heisenberg uncertainty principle, it is telling us what? It is telling us the uncertainty in position, the uncertainty in momentum, that becomes too small to be considered. Okay, so that is negligible. So it is significant only for microscopic objects. Okay, macroscopic, like a football, tennis ball, anything that's in motion. All right. Next, we move to our question. So that was asked in NEET 2017. The question says you have to pick the wrong statement, the incorrect statement. Okay. First statement is the uncertainty principle is delta E into delta T greater than equal to h upon 4 pi. Now, please don't get confused and think this is temperature. Okay, it is indicating times. Generally, in chemistry, what we'll have, temperature will be denoted by capital T. Macroscopic means the bigger objects, not the subatomic particles. Okay, which can be seen with naked eyes. All right. To solve this question, do we just keep on solving each and every option? That is one way. That is the longer version of it. Or what we can do is we can read further. Okay, let's read further. Okay, right now I can gauge that you do not know this one. Okay, this is still under. We need to consider it again. We do not know about this. Let's move to the next one. Half-filled and fully filled orbitals have greater stability. Half-filled and fully filled orbitals have greater stability due to greater exchange energy, greater symmetry, and more balanced arrangement. We know this statement is true, right? This statement is very much true. It is correct. Okay. The next is the energy of 2s orbital is less than the energy of 2p orbital in case of hydrogen-like atoms. Yes, B is correct. So, is the C option correct or incorrect? For hydrogen-like atoms. Now, people, you need to understand, everybody, the energy difference, the difference in energy of the orbitals that we consider, no, the Aufbau principle that is there, it is for atoms other than hydrogen-like species. Okay, for hydrogen-like atoms or hydrogen-like ions, what we will take, the energy is only considered. Okay, listen to me. The energy is only considered on the basis of principal quantum number. Okay, only on the basis of principal quantum number. So let's look at the statement here. If two orbitals have the same principal quantum number, that is this value of small n, have the same principal quantum number, then their energies would be the same. Then they have equal energies. Okay, so for a hydrogen-like atom, what we can say is 2s is equal to energy in 2p. Okay, and 3s equal to energy in of 3p equal to that of 3d. We just have to look at this value of small n, the coefficient that is there, no? That's it. If it is the same, the energy of the orbitals will be taken to be the same. Priya, it is simply only for hydrogen-like atoms. See, hydrogen-like species will have, only one electron, right? That will reside in the 1s orbital. Exactly. So 1s orbital will have lesser energy than the second shell, than the third shell. This is not there. So all the second shell orbitals, all the orbitals which are residing in the second orbit will have equal energies. Okay? Is it clear? Okay. So it tells me that the C option is incorrect. This is false. So that is my correct answer. You need to understand that. Let's look at the D option as well. De Broglie's wavelength is given by lambda is equal to h upon mv, where m is the mass of the particle that we are considering, and v is the group velocity of the particle. So that this is obviously true, right? We know this is direct statement here. Okay. The next is uncertainty principle. Now, how do we know this option A is correct or incorrect? Okay. How do we know this? Now, the uncertainty principle is given by what? So let's go back to our uncertainty principle. It is given by delta x into m delta v. We can write down this greater than equal to h upon 4 pi, right? So what have we concluded here? Delta x into m delta v greater than equal to h upon 4 pi. What do we have given to us? Delta e into delta t is greater than equal to h upon 4 pi. So we need to understand whether the LHS here and LHS here is the same or different. Okay, so let us understand how do we do that. What is this? This is energy. Now we know the particle is in motion, right? Very good, Priya. Particle is in motion. So what do we know? It will possess kinetic energy, and that can be written as half mv square. Now we need to put this uncertainty symbol again. The mass of the electron will be the same, mass of particle will remain constant. So we will have delta V here, right? So we can put here delta V ka square into delta T greater than equal to h upon 4 pi. All right. Now, simple maths, what do we know? The speed of a particle is equal to distance upon time, right? Speed of a particle is distance upon time. So I can say delta V into delta T equal to delta X. We can say that, right? So let us put it here. So this becomes half into M into delta V. I am now going to write down delta V into delta T as delta X greater than equal to h upon 4 pi. So is this similar to our equation here, right? This is similar to our equation here. Delta X into M delta V we have gotten. Delta X into M delta V we have it here. All right. So it tells me that this statement is actually true here. So the incorrect statement, we had to figure that out. The incorrect statement is option C. Done, everyone? Next, we will move to the next further question. This was asked in NEET 2014. Okay. Calculate the energy in joule corresponding to light of wavelength 45 nanometer. So whatever is given in the question, keep on writing down that data. Lambda wavelength is given to us as 45 nanometer. Now, how do we convert nanometer to meter? How do we convert nanometer to the SI unit? We multiply by 10 to the power minus 9. Okay, we multiply by 10 to the power minus 9. So that is Planck's constant is given to us. So this was a very easy question. All the information is provided to us in the question. If we remember the basic formula, we would be able to solve this. Okay, very nice, very nice. So Planck's constant is H equal to 6.63. Exactly, it is 6.626. If it is given, okay, Jayant, I'll try to give that later on. If it is given in the question, we can use 6.63 here into 10 to the power minus 34 joule second. Please remember this this unit of Planck's constant as well. Okay. Speed of light is given to us as 3 into 10 to the power 8 meter per second, but we should also remember this value. Okay. So this is very easy question. What do we need to calculate? We need to calculate the energy, right? So energy is equal to hc upon lambda. We know this, right? E is equal to h nu. So we can write down E is equal to hc upon lambda. This is simple calculation that we need to perform, right? So H is given to us 6.63 into 10 to the power minus 34 joule second into C is given to us as 3 into 10 to the power 8 meter per second, right? Lambda is given to us as 45 into 10 to the power minus 9 meters. Please remember to convert this nanometer into meter. Otherwise, you will not get the correct answer. Okay. So if you calculate this, it's going to come out to be 4.42 into 10 to the power minus 18. Okay. So I hope you will be able to do the calculations. Right. So, okay. So yes. So this is a very basic question directly based on the formula. So again, note it down. It is a very important formula for us. E is equal to hc by lambda and it is equal to h nu. It's a very important formula. Okay. Next we move to a question asked in NEET 2013. Okay. Let's look at this question. Based on the equation, E is equal to minus 2.178 into 10 to the power minus 18 joules, Z square upon N square. Z is the atomic number. Okay. N is the number of the shell that we are talking, number of the orbit where the electron is present. Now, this formula you have seen in NCERT as well, right? Certain conclusions are written here. Based on this particular formula, certain conclusions are given to us. Which of the following is not correct? Again, we have to look at the incorrect answer, an incorrect option. Let's read them one by one. This equation can be used to calculate the change in energy when the electron changes orbit. Change in energy meaning delta E we need to calculate when the electron is changing orbit. So from one orbit, let's say N1, it is moving to another orbit. Let us assume N2. Okay, so all of us know we can very well calculate it here. We can put E1, we can put value of N1, calculate E1, then we can put N as N2 and calculate the value of E2. All right, so that is very easy, and this is statement is true here, right? This statement is true. Next we move to the second option. For N equal to 1, the electron has a more negative value of energy than it does for N equal to 6. Pay attention here. When I put N equal to 1, this formula becomes E equal to minus 2.178 into 10 to the power minus 18. Z is the same, right? N we are putting 1. Right? So this becomes 1 ka square, which is again 1. Right? The another value of N that is given to us is, let's calculate E6 here. So this becomes minus 2.178 into 10 to the power minus 18 into Z is same for both, and this is 6 ka square. Correct. Now it tells me that electron will have a more negative energy. So you can easily see that E1 is more negative as compared to E6. Right? E1 is more negative as compared to E6, that we can see here. Here it is 36, here it's just 1. Right? So the first part of the second statement is true. The B option may first part is true. Let's move to the second part. This means that electron is more loosely bound in the smallest allowed orbit. Okay, even if we do not remember this formula, like it's not given in the question, how do we understand this particular statement? It says if an electron, if this is the nucleus, okay, if electron is present in the smallest allowed orbit, this is the first orbit, smallest allowed orbit, then it is telling us that it is more loosely bound. Right? It is telling us it is more loosely bound. Then let's say another orbit that is N equal to 6 given to us. This is N equal to 6. This is N equal to 1. So is this statement true? It is more tightly bound, right? The distance is less, so it is more tightly bound here, right? Guys, focus on the session, Paras. Okay, so it is not more loosely bound, but this should be more tightly bound, right? So this is the incorrect statement. This second part of the statement is false. Okay, let's look at the option C. The negative sign in equation simply means that the energy of electron bound to the nucleus, when an electron is bound to the nucleus, that energy is lower than it would be if the electrons were at infinite distance from the nucleus. Let's put the value here. This says, if let's say electron is bound to the nucleus, it is in some attraction with the nucleus, okay, then there will be some particular energy possessed by that electron. Okay, a particular amount of energy possessed by the electron. And the other condition that we are comparing it with is when the electron is present at an infinite distance from the nucleus. Okay, infinite distance from the nucleus. We need to compare those energies. So we will just see if I put N equal to 1, let's suppose. Okay, let's suppose we put n equal to 1. Then we have written it here. This is the value of energy that we get. This value. Whereas if I put n equal to infinite, okay, infinity, then what will happen? Whole of this term will become what? What will this become? This will become 0, right? So that means E, when I have infinite, this becomes 0. Okay, anything over infinity would become the, here it would become 0. Now, so the statement is definitely correct here. This E1 is lower in value as compared to the energy when electron is present at an infinite distance from the nucleus. Clear? So this statement is true. Let's look at the last option that's given to us. Larger the value of n, larger is the orbit radius. So this is very much clear, I suppose. If this is my nucleus, this is n equal to 1, n equal to 2, n equal to 3, right? N equal to 2, n equal to 3. As the value of n is increasing, as the value of principal quantum number, or the here we have the orbit number is increasing, the radius is increasing. So this is a very simple statement. So this is also true in nature. So there is only one incorrect statement, that is this one, option B. So that's our correct answer here. Understood? Very nice. Let's move to the last question of today's session. This was again asked in 2013 and it's also a very easy question. You will tell me the answer now. The value of Planck's constant is 6.63 into 10 to the power minus 34 joules second. The speed of light again is given to us, but just pay attention 1 second. This is 10 to the power 17 in nanometers. Okay, this is in nanometers here. Okay, which value is closest to the wavelength in nanometer we need to calculate of a quantum of light with frequency of 6 into 10 to the power 15 per second. So we have been given the value of h, we have been given the value of c. Okay, and we are given nu is equal to, nu is frequency, is equal to 6 into 10 to the power 15 per second. Okay, so that's very easy. Which formula will we use here? Which formula do we need to calculate? Do we use here? Do we apply here? Will you stop fighting? Okay. All right. So we need to calculate the value of wavelength. Can you all do that? It's hc equal to nu. Okay. All right. So we have these, formulae. One is E equal to h nu, one is E equal to hc upon lambda, right? So I can put h nu equal to hc upon lambda, or simply we have c equal to nu lambda, right? We need to calculate lambda here. So lambda can be calculated as c upon nu. So you can calculate the correct answer there, right? Simply you need to calculate the answer. All right. Exactly. C is equal to nu lambda we will use. Right. So understand that this is also given in nanometer and we need to calculate the wavelength also in nanometer. If the speed of light would be given to us in meters, then remember to convert it into nanometer. Okay, so pay attention to the units always. Okay. Now, the last thing that we can study here is about de Broglie wavelength. De Broglie's wavelength. Okay, so we know that de Broglie gave us a formula which says lambda is equal to h upon p, that is h upon mv, right? This is the momentum which is given by mass into velocity. Exactly. But we need to remember the physical significance of the lambda here, de Broglie's wavelength here. So this actually explained the dual nature of particles, of matter basically, dual nature of matter. So it told us that similar to photons which have particle nature as well as wave nature, electrons will also have both kind of natures. the particle nature will also be exhibited and wave nature will also be exhibited. Now, questions have been asked upon the physical significance of this de Broglie wavelength. The physical significance is, it says, all the objects, yes, all moving objects, exactly, very nice. All moving objects emit, like they have some wave nature. All moving objects possess a wave character. Okay, but for larger objects, for normal objects that we have, they have, the mass is very high, right? The mass is high. Therefore, lambda is too short, or we can just say this is very small. Therefore, for larger objects, the wave character cannot be detected. The wave character cannot be detected. All right. So, but the subatomic particles like electron that we have, it has very small mass, right? So the wave character can actually be detected, and thus we have this formula. So we need to remember this point. Okay. All right, everybody. So in the next session, we will be talking about electronic configuration, and I hope you guys will come prepared with all your quantum numbers, right? And the quantum mechanical model that we have. Okay, so hope to see you guys there in the next session. Till then, all the very best for your preparation. Bye-bye, everybody.